This is Unit 3, Continuous Distributions and Confidence Intervals. Topic 1, the Uniform Distribution. In this unit, we're going to take the binomial distribution and we're going to take it one step further. In statistics, we deal a lot with continuous probability distributions, and those distributions are key to aspects of statistics such as confidence intervals as well as hypothesis testing. We have 9 topics in this unit, and we will be covering 3 this first week. So just again as a reminder, discrete distributions. Last time we looked at 2 different types of distributions for discrete data. A probability distribution, which isn't necessarily a statistical distribution, it's just a way to describe data, as well as the binomial distribution. There are actually a lot of different probability distributions for discrete data. Some of these are, and we won't be doing any of them, it's just important to understand that just because we didn't cover it doesn't mean that it doesn't exist. So the hypergeometric distribution, the multinomial distribution, the negative binomial distribution, and the Poisson distribution. The Poisson distribution is actually one of my favorite. It's pretty cool. The rest of the distributions are all just specific ways to investigate specific situations in statistics. So just like how we had the 4 requirements for the binomial distribution, each of these have their own, well, the first 3 have their own similar set of 4 requirements. Poisson is kind of on its own, but it is pretty interesting. So this unit, as I said before, we are going to move into continuous distributions. The 3 that we're going to be looking at are the uniform, the standard normal, and the normal distribution. So again, continuous data are things where if we had more and more accurate measuring devices, we could get more and more decimal places. So times, distances, and heights are usually how we think of those, but traditionally they're values that are measured. The uniform distribution is the distribution that we're going to begin with, and that is the focus of this topic. The uniform distribution is very unique. We are going to be treating it as continuous here. All of the outcomes in between a range of a maximum and minimum value are equally likely. So that means that the probability of any value at all is exactly the same. Well, sometimes we use the uniform distribution if we just know nothing at all about our scenario. It could be nicknamed, depending on where you are, as the know-nothing distribution, because if you don't know anything at all about a certain scenario, you may just assume that all outcomes are equally likely at first, and then usually find out more information and modify your distribution as you go. There are a number of examples of the uniform distribution in real life, but in general, this isn't something that applies a lot, but it is going to be very helpful to us for the rest of this unit. So a discrete version of this distribution would be the results of a die roll. So for example, if you roll a die, you can get 1, 2, 3, 4, 5, or 6, and as long as the die is a fair die, we assume that they are all equally likely outcomes. So if we kept on rolling a die over time, we would eventually expect to find that the probability of getting each of those 6 numbers would be exactly the same. The location on a tire where the next puncture will occur, so of the strip of tire that touches the road, in general, that is uniformly distributed. If you think about each location like an XY coordinate on the tire. And then the position of an air particle in a room. So as you can see, I mean, we're kind of stretching a little bit, but when we get to the next topic, we will be very grateful that we had the uniform distribution under our belts, because it makes us able to understand what we're doing with the normal distribution at a much deeper level. So the uniform distribution has a number of different characteristics that we're going to want to be familiar with. First, the graph is a rectangle. So we actually would have seen a uniform distribution in topic 1, where we were looking at matching graphs with their descriptions. So it's a rectangle. The area of the rectangle and probability are synonymous. We'll find that that is going to be a very, very handy key aspect of the uniform distribution. The area of the rectangle is 1, and this is because it is to represent 100% of all possible outcomes. The mean, which we're going to start to think about as the expected value, is mu equals a plus b divided by 2. The standard deviation, again, not something that we can understand. It's just a formula that we need to remember. It is sigma equals b minus a over the square root of 12. And lastly, the picture for the uniform distribution. All of our distributions that we're going to be dealing with from here on out are going to have their own picture shape. So some of them are going to vary depending on different pieces of the problem, but the uniform distribution is always kind of the same. It's nice and friendly and familiar. So a generic version of this, and this is generic because it doesn't have any specific numbers filled in. It just has the, A and B for our letters. So just like we have 2 axes in regular math class, we're going to have 2 axes here. So this bottom axis is the x-axis, and this is whatever your variable is. So when we were doing probability distributions, the variable was some value, maybe 0, 1, 2, or 3 people admitted to texting while driving. Well here, this variable x is going to be whatever we are measuring. So it could be the time, height, and distance that we had talked about when we talked about continuous. The vertical axis is the probability that x happens. So however high we go up here, so let's say this is right in the middle of A and B, this is my number I'm interested in. If I head up to the top, I head over to the left, the probability that we end up getting on this tick mark is always going to be the same for any single possible value at all. So the lowest possible value that we can get is A, whatever that number is in our specific example. The highest possible number is B. The height of this is A divided by 1 divided by B minus A. And so when we look at a specific example of this, we'll make a little bit more sense of it. But this distance, let's say this is 2 and 10. This distance would be 8. So in order for this area to end up being 1, this would have to have a height of 1 over 8. So length times width, the same way that we've always found the area of a rectangle, is the same thing that we're going to be using here. So right now it is pretty vague. We'll get to a specific example coming up, and we'll get a chance to kind of get a better understanding of these pieces. So before we do that, there are 2 reminders that we should have. So just like how the normal distribution started as a histogram, and then the class widths became smaller and smaller until a line went over top, the uniform distribution is formed the exact same way. So let's say, I don't know, maybe this is test scores. This would be really bad if everybody scored with a similar probability between, let's say, 0 to 9, 10 to 19, all the way up to, I don't know what score, let's pretend we make it up to 100. So if we had originally had these bars across, and then we eventually said, okay, I'm going to make the classes smaller and smaller and smaller until I do get a straight line exactly on top. So the uniform distribution began the same way, but it just seems a little bit different because not a lot of scenarios are uniformly distributed, and we can't do the die roll example with this because there's not any numbers in between 1 and 2 that you can roll on the die. But it began just the way that a normal distribution does a histogram, where the classes got smaller and smaller along the bottom until eventually there was just a smooth line over top. So let's look at an example. Suppose that the amount of time it takes to commute to work, barring accidents and other non-typical delays, follows a uniform distribution. The minimum commute time is 22 minutes and the maximum commute time is 28 minutes. This is a situation that would definitely follow a normal distribution. I'm just about positive. It may be skewed in one direction or another, but it would probably be pretty bell-shaped. But for now, we're going to assume that things are uniformly distributed, but it will be worth it when we go to find probabilities for the normal distribution sections. So part A says complete by filling in the picture with the 3 missing values and label the axis. So you'll always get a blank distribution that looks like this. So there is the normal rectangle shape. It's never going to be drawn to scale because this height would have to be really short. So it's going to be the same picture every time. You'll just have to remember that it's not drawn to scale. So the first thing that we're going to need to do is label the axis on all of these, which is minutes. So this is the commute time in minutes. The low number and the high number are going to go on the low tick mark and the high tick mark of the rectangle. So for this example, that's 22 and 28 minutes. So now what we need to consider is that the area inside here is 1. So the question you have to ask yourself is, if this has a distance of 6, 6 times what number gives you 1? So this is my distance of 6 here. And the answer to that is going to be 1 over 6. So if you found the area of this, 6 times 1 over 6, the 6's would cancel out, and so you'd be left with an area inside here of 1. So next we want to answer questions using our distribution. B says find the probability that the commute time is less than 24 minutes. And this is when we want to use the item in that general info for the uniform distribution that said area and probabilities are synonymous. So basically they're interchangeable, they're exactly the same. So here is a picture of this scenario. So here we would have 25 would go right smack dab in the center. 24 would be a little bit less than that. So the area of this box is equal to the probability that the commute time is less than 24 minutes. So once you set up your picture, all you're doing is finding the area of rectangles. Of course, setting up the picture is going to be the more challenging part, especially with this 1/6. But once you've got the picture going, you're pretty much good to go. So if we took this little rectangle and we pulled it outside, it would be a distance of 2 along the bottom, and the height of this is 1/6. So this height is 1/6. So this height is 1/6 as well. So the area of this box is going to be 1/6 times 2. That's 1/3, which is 0.3333. So the probability that the time to commute to the whatever you're commuting to is less than 24 minutes is 0.3333. C says, find the probability that the commute time is greater than 25.5 minutes. So the first thing that you're going to want to do here is label your picture. So 25 minutes fell right around halfway. So my mark is a little bit to the left there. But the probability that the time is greater than 25.5 minutes would be 1/6 times 2.5, because that's how long this distance would be. So if this was 25.5 here, I would have 26.5, 27.5, and then another 0.5 to get up to 28. So the height of 1/6 times 2.5 would be 0.4167. So once you set up your rectangle, it comes down to setting up the dimensions of your box and then finding the area of it. Find the probability that the commute time is between 23 and 26 minutes. Well, when you draw your picture, this one is a little bit more to scale. This rectangle is exactly half of the whole bigger rectangle. And the reason that I know this is because I have calculated that this is a distance of 6 along the bottom. The box that I've drawn has a distance of 3 along the bottom. So this looks like about 1/2, and it should fall around 1/2. So the probability that the time is between 23 and 26 is 1/6 times the distance of 3 along the bottom, which would be 0.5. So this is a probability. It doesn't have any units with it at all. That's one thing, is as we go forward away from the probability unit, probabilities start to get, I don't know, like minutes or something is something that someone might accidentally say on there. So definitely make sure probability is just a plain old decimal value between 0 and 1. Lastly, find the mean, which we're going to call the expected value pretty frequently, and the standard deviation of the commute time. So the reason that we're calling the mean the expected value is because the mean is the measure of center. It's one number that we're using to summarize them all. So it makes sense that if we were to say, hey, if you had to pick one number that would happen from this distribution most often, which one would it be? Well, if it was a uniform distribution, you'd have to tell them that they're SOL. But the mean is still, if we had to pick one number, we would use the mean. So the mean is going to be 25 minutes. It is smack dab dead center in the middle of your distribution, which makes sense. If you had to pick a number, pick the one that's exactly dead center. The standard deviation, as always, doesn't really make specific sense. It's just a formula that you're going to have to follow. So the standard deviation is b minus a divided by the square root of 12. So that would be 6 over the square root of 12, which would be 1.7 minutes. There is a second example here for this section. I'm going to just leave this PowerPoint and the work up to you. It is exactly the same as this previous example. Setting it up is going to be key here. So please feel free to email me if you have any questions.